we all find that? So find this page here. No, I'm screwing up. My bad, Cam. My bad, everybody. We want the tasks. Find this page. So let me come up here. Yeah, so it's this one here. Module 2 says more quadratic functions, task packet. That's the packet we want. And then what I was saying is, we've been reviewing this now for the last few days. You took a little test on it. Hoping we can do that reasonably well. So we're skipping along to, finally, this guy. This is where I want you. Okay. Okay, so from here, let's go ahead and go through this. What this is asking you to do first is just complete this table here. So you're dealing with this function, y equals x squared. We're going to go ahead and graph it, and then we're going to talk about these features. So we're going to do a little review anyway. That's why I also felt fine skipping over those first couple questions. So let's just fill in this table. Pretty straightforward. The function that we're going to be graphing is this, and that's what we're going to be filling in the table for. So whatever x is, you're simply squaring it. So for -3, if I take this -3, plug it in for x, and I would square it, then we would get 9. -3 times 3 is a 9. Take your -2, if we plug that in for this equation here, square it, -2 squared is a 4, -1 squared is a 1, 0 squared is 0, and then just fill this in. 1 squared is 2, 2 squared is 4, 3 squared is 9. Really? Once you have those, go ahead and graph those points. So you should have, how many points we got there? 7 points. Go ahead and plot those points on your graph. Why is it doing that? So I'm going to make it a little bigger. All right, so -3. All right, so those are our 7 points. We should know this is a quadratic equation. You would have had that question a number of times. So Bisher, you don't have to. So if I take you back to our Canvas page real quick, this is what I was mentioning before. If you wanted to print out all that packet, you could right now, if you have a printer. Here's what this is on an individual day. If you didn't get the packet pickup, so Bisher, if we had the packet pickup, this is one of the things you would have picked up. If you don't have that, and you don't have a printer, then you just need a blank piece of paper. So we get our parabola, we get our U-shaped graph like we knew, because this had an x squared term, so we should have known this is a parabola, and this is our graph. We'll talk more specifically about what this means in a minute, but in parentheses here, what I'm highlighting, we're going to call that our parent graph, and we'll talk about what that refers to here shortly. Not important right now, but that's our parent graph, and it's our y equals x squared graph. All right, some things that we talked about a little bit in passing last week. We dealt with it a little bit, but we're going to now go through this a little bit more. If I ask you to define the domain for this, these are our x's, those are our y's. Do that real quick. So see if we can do the domain of that graph and the range of that graph. All right, our domain. Nora, what do you think for the x's? I can't hear Nora. Can you hear Nora? Oh, okay. Yeah, you're muted.
Negative infinity.
Good. This will go left and right forever. Even though it goes up pretty quickly, this is going to continue to go to the left forever and ever and ever. So we go left, we go right. The range then are the y values that we're going to hit. So we want to go, what's the lowest y value to the highest y value? All right, anybody confident in their range here? All right, who's that? Bisher, what do you got there, bud? It is. Infinities are always parentheses. And what do you think about the zero, Bisher? A parentheses or a bracket? Why do you think it's a parentheses? How do we differentiate?
Because, I don't know, like ones and up, they have parentheses. I don't know, they have brackets.
Okay, so let's look at this point right here. Do we actually... It is a bracket, good, because we actually do get the y value of 0 right here. When we say the y value of 0 actually exists in our graph or in our function, then what that means is we have to close that it is a defined value on our graph. Okay, so good, 0 to infinity. All right, we dealt with this a little bit in terms of where do we increase, what interval do we increase, and that means as we move left to right, are the y values increasing or decreasing? So we can see a little bit in our table, see how we're decreasing, but then eventually we start to increase again. We want to now define it for every x value, not just the x values here in our table. So we decrease for a little while, but then we start to increase again. So if we look at our graph, let's just move left to right. As we look at our graph, notice how our graph, our y values would be getting smaller over here. We're at 9 up here, then 4, and then 1, and then 0. So we're decreasing this entire time. So everywhere to the left of 0, we're decreasing. So we would say, let's do the decreasing one first. From a negative infinity, these are always x values. Our interval of increase and decreasing are always defined in terms of x's. So from a negative infinity all the way up to the x value of 0, we are decreasing. After 0, though, we should hopefully see that our graph is now going to start increasing. It's starting to go upwards again. So we would start to increase at 0. That's when we started to increase. And we continue to increase forever after that. So 0 to infinity. All right. Max minimum. We talked about this a little bit briefly. It's nothing I tested you on yesterday. We just talked about it a little bit because we're going to deal with it a lot now in this chapter. If I now ask you to look at that graph and you tell me if we have a maximum or a minimum, circle one of those. I think we can all do that on our own without me telling you. So look at this graph and identify, is there a maximum there or a minimum there? And hopefully that's pretty obvious. So a high point or a low point. And then I don't think I need to ask anybody. Hopefully we know there's a low point in that graph. There is no maximum. The graph just keeps going up, 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 and up. So we just have a minimum. We now, as we start dealing with these parabolas, these quadratic equations, we're going to give that maximum or a minimum, in this case, a special name. So that name is called a vertex. So this point up here, the minimum on this graph, that is what we will start using the phrase vertex for, or the word vertex for. The high point or low point of our parabola is called a vertex. The other new word. So we have a few new words here today. The parent graph, we haven't alluded to that fully just yet. We'll talk about what that means more here in a minute. The other new thing is the idea of a vertex, the high point or a low point in your parabola. We also have what we call a folding line about a parabola. So we'll talk about that in a minute, but what that is called, so a new little word / phrase, is what we call an axis of symmetry. So last year in Math 1, you would have done a lot of lines of symmetry. You would have done those constructions where you're folding things up around a certain line and the graph lands on top of them. So if you look at our axis of symmetry, two ways to think about this. So notice our vertex, which right now, I already have highlighted. I lost my 0 there. So let me highlight this. Here's our vertex, right? If we come over here, do we all agree our vertex is at the point 0, 0 right now? All right, that's the point where we have our vertex. Okay, so here's what it means by symmetry. Look at the point directly in front of the vertex and directly behind. Notice how those give you the exact same value. They're both 1s. If we look at the point 2 steps in front and 2 steps behind, notice how those both give you the same value. And then we get a 9 here, we get a 9 here. So there's what is called symmetry about this point of the vertex. What that means graphically, if I go to this graph, I'm going to try to use blue here, is if I draw a vertical line right down the middle of this parabola, again, you got to remember some symmetry ideas from last year. Would we agree? So if you do it on yours might be a little neater than mine. I'm not an artist. Would you agree then that if we folded your paper up right now around my purple line, that the right-hand side and the left-hand side of those parabolas would land right on top of each other? Okay, and that's something you would have talked about a little bit last year in Math 1. So that's called that point that cuts our parabola in half, basically. If you think of it that way, it's cutting our parabola directly in half, and then we can fold it around. That is what is called an axis of symmetry. It's our line of symmetry last year you would have talked about. So instead of saying line of symmetry, we're calling it the axis of symmetry. Okay? So some new words there. Okay, so next thing. If you have a graphing calculator, great. If not, I'm going to show you on mine. It says using a graphing calculator, you're going to explore other quadratic equations in vertex form. So we'll talk about vertex form here in a minute. But this is notice how we have the square term right here? That means it's a quadratic function. So this should give us a parabola, a U-shaped graph. For each parameter, A, H, and K. So notice how there's an A right here, there's an H right here, there's a K right here. Each of those gives us defining characteristics about our graph. Identify how the parent graph. So the reason this is called a parent graph, everything is based off of that graph. So everything we do, we're going to compare it to our parent graph. That's the original graph. All right, everything comes from that. See how that parent graph is changed when we change each of these parameters and how that's going to alter your vertex, your axis symmetry, domain, range, all that good stuff. So the first thing we're going to start with is the letter A. So if we look up here, notice where the A is at. The A is the number that's going to be in front of your X. All right. So that's our coefficient. Since it is a coefficient, start with positive values that are greater than 1. Then check what happens to the parabola with positive values less than 1. All right. Notice we're dealing with this function. All right. So jump down to here. And I'm going to put this onto our calculator real quick. So I'm going to graph our parent graph right now, the one that you have on the previous page. And we should see our parabola. So this is what we just graphed. That's our parent graph. What I'm then going to have you do is if we go to this function, let me change this. So in your table, our parent function right now is y equals x squared. That's this one. Wrong color. That's the one that I have on my calculator. That's the one that you have on your piece of paper. Right now, this has a coefficient of 1. So there's just a 1 in front of this. So what we're going to do is we're going to give it a coefficient of, of 2. So put a 2 right here. I'm going to graph that on my calculator. And then I'll do the 3, and you're going to tell me what happens to our graph. So real quick again, here is our original graph. It's the blue graph. All I'm going to do is underneath the second one, I'm going to put a 2 in front of that x squared term. All right. The paper said guess what's going to happen, so you don't necessarily need to write it down on that previous step, but something's going to change in our graph. So the question would be, what's going to happen to our graph if that 1 becomes a 2? And in fact, let me just go up here so we're clear. The parent graph has a number of 1 in front of it. So we're going to change that 1 to a 2. And this should be the red graph. So then talk about determine what's going to happen to our graph. All right, so here we go. Here comes the first one, the one that you have on your paper. Here comes our second one. Is that still a U-shaped graph, first of all? Yeah, so it's still a parabola. It's still going to look like a U. But what we want to talk about then is what is different about this. So if you look at in here, it said, how did the graph of y equals x squared and its features change? So before we talk about that, let's throw in a bigger number. So now I'm going to do 3. So again, instead of y equals x squared, like we've already done, we're now going to put a 3 in front of this. So if I go back in my calculator, this one is going to graph black. So the black one will be the third one. And we're now just going to put a 3x squared. And here comes the black one. Still a U-shaped graph, still opening upwards, but it has changed the original blue one a little bit. All right. Yeah, Cam?
Why is it smaller? It's a bigger number than x, right?
That's a very good question, Cam. Yeah, that's a very good question. So let's write that down, actually, because that's one of the things that we want to get at. He said smaller. So let's put it this way. Y equals x squared, in Cam's words, got smaller. I probably wouldn't say smaller. That wouldn't necessarily be the word that I'm using, but I think a lot of you would use that word. I think you understand what Cam is saying. Okay? What we would probably say as fancy math teachers, we would say that guy got compressed a little bit, right? It got squeezed. It was wide and it got squeezed a little bit. All right? So Cam asked why, and that's what we want to put. So definitely put this. That's definitely what we want to be putting down. Our graph got compressed. So Cam asked why, because in Cam's mind it's counterintuitive, right? You wouldn't think that happens. So let's go to our table real quick. Think about what happens then, Cam, if I put a 3 in. Let's just do a 2, so it's smaller. So when I get this x squared value, wouldn't I now be multiplying 9 by a 2? So now I'm up here at 18. So let's do one more. If I put a 2 in front of the x squared instead of a 4, now I'm going to get 2 times 4. That's going to be an 8. So that means this point here is now 1, 2, 3, 4, 5. All right. Here's 5, 6, 7, 8. If I were to go to this 3, now I'm at 18. So 1, 2, 3. Now isn't 18 way up here? You can't even really see it. So what that does to hit these points, doesn't that make our graph now a squeezed, compressed version of what it would have been before? So putting a bigger number in front of that makes our numbers grow quicker. And because our numbers are growing quicker, it's squeezing our graph really, really tight to each other. All right? Does that help a little bit?
Yeah, that helps.
Okay.
Could we, I know it's not on here, but could you try putting like a 4
Sure.
in your calculator? Let's see what happens with that.
So we do 4. So this will be pink. If I can reach the 4. Nope. Try that again. So this is pink. This is now going to be really squeezed in there even tighter, right? Yeah. All right. So good. So now, if you had to guess, Cam probably would have thought that's not what would have happened. So now that we've actually seen this, let's start throwing some of these in here. This is actually 4.5, right, Cam? So 9 divided by 2. So we kind of did that one already. So that's actually 4.5. I'm actually going to cross that out because the way I have these notes set up, it almost should go right here. So let's get rid of that one. Because now all of these, we're going to write what happens in this box. So now we should have at least an idea of what's going to happen. So let's go to the calculator. I'm going to leave the parent graph in there only. So I'm going to clear this one, and this one. And the first one that I want you to graph or look at is 1/2. So if the original value is a 1, I'm going to enter it as a decimal. You can reach it, so 0.05. That's our Sorry, I don't need the O. So 0.5 x squared. Do we agree that the one now got smaller versus bigger? So if we're kind of following Cam's line of thinking, he thought, and I would imagine a lot of you did, if this number got bigger, it would make our parabola bigger, like wider, correct? But it actually made it compressed or smaller in Cam's word. So if we make our numbers, okay, so now if we're following that line of thinking, now Cam is saying most likely then this is going to make this one wider. So here's our original graph coming in, and here's the one with the smaller value. Did that make it wider? Yeah. Okay, I'll show you one more, but I think hopefully having seen this, we understand that. If I throw a 1/3 in front of this, let's compare 1/3. 1/3 is 0.3. Do we all agree 0.3 is smaller than 0.5? So that, if we're understanding, should be even wider than the previous one. So we throw that in there. And that guy's even wider yet. Okay, so when we start putting numbers in smaller than 1, our graph gets wider. Okay, so let's write that in there. Y equals x squared gets wider. So our parent graph gets wider. So to summarize, let's do it kind of in bullet notation. A equals 1 is our parent graph. That's the original graph that we're basing everything off of. And by this equation here, I'm talking about this equation, A is the coefficient. So let me see if I can squeeze an A right here. So A is the number in front of x squared. If A equals 1, that's our parent graph. If A is greater than 1, so these guys up here, so if A is greater than 1, our graph gets compressed, squeezed. Smaller is not necessarily wrong, but I think these words illustrate a little bit better what's happening there. We're squeezing that thing tight. Now we're going to add a little something here. We're definitely going to say if A is less than 1, but we're limited here. We can't just say less than 1 forever. We're going to say if A is less than 1 for sure, but we also need to be greater than or equal to 0. We have to be between a 0 and a 1. And just let me show you why that is, although you should probably have an idea. If I graph, so let me get rid of these. If I graph 0, if I can reach it. So if I graph 0, x, come on you. What do we think this is going to be? Is this going to be a parabola, we think? Mystery here. Let me hit graph. Here's our original graph. See how that's just a horizontal line? Because it's always 0. You're multiplying by a 0. So 0 doesn't work. So what we want to then put is 0 is not going to work. I don't know why I have the equal sign there either. So let me erase it. All right, then our parent graph gets wider. All right. All right, then real quick, hopefully we can get this done in the next 5 minutes. Now check to see what happens if our A is going to be negative. So we're still going to have this original y equals x squared. What I'm going to do is a -2. So here's y equals x squared. Form some guesses in your head of what might happen here. So I'm going to do -2x squared. Anybody have a guess what happened here? Brave. Walker?
I think it's still going to be parabola, but it's going to be like upside down.
All right, so let's see. Walker says it's still going to be a parabola, which would make some sense. We have this squared here, and I've said we always get a parabola with the squared, so that's good. He thinks it'll be upside down. So let's graph it. There's the original. And is Walker correct? Did it go upside down? Yeah. There's one other thing we want to notice. The value of 2, don't worry about the negative sign. The value of 2 is bigger than 1, correct? So if we really look at this closely, not only does it open upside down, would we agree that the red one is squeezed a little bit tighter than the blue one? Because the value of 2 is still bigger than 1. The negative is just flipping us around. All right, so when we now go to here, our quadratic function that we're dealing with is now a negative 2x squared. And when we have that negative coefficient, so if a is a negative number, the graph is upside down. Now notice, it was also squeezed when the 2 is bigger than a 1. So we also still squeeze that thing. So it's a tighter looking graph. All right, jump to the negative 4. So let's do a negative 4x squared. If what we just talked about is correct, then what should happen, this one should still be upside down. And this one should be squeezed, for lack of a formal word, even more than our previous graph, because the 4 is bigger than a 2. So if we confirm that, so we'll leave the negative 2 in there. All the negative is telling us we're going to go upside down. The value of 4 is bigger than the value of 2, is bigger than the value of 1. So this should be very, very squeezed, all right, really, really narrow. But it should still open down and it should still be a parabola, like Walker said. All right, so the bigger the overall value, the tighter it is. If it's negative, it's going to go down. So then real quick, let's do one more before we lose time, run out of time. Let's do this guy, y equals a negative 0.5x squared. So compared to our parent graph of 1, the negative definitely has us going down, so that's not going to change. But hopefully we would agree that a 0.5 is smaller than a 0.1. And like we said at the top, if we're less than 1, our graph should get wider. So then real quick, let me show you, and we'll confirm that. So I'm going to do a negative 0.5x squared. The negative should open us downwards. 0.5 being smaller than 1 should make it wider. So we'll see if that's confirmed, see how much wider it is in every other graph there, because 0.5 is the smallest value on our list right now. All right. Okay, so summarize what happens when a is a negative. We can hurry up and get this done. We'll say the parabola will open downwards. All right, is what's going to happen when your a is a negative. And then again, the bigger the number, the tighter it is, the smaller the number, the wider it's going to be. All right, perfect time to stop because the bell is ringing. All right, so we're going to say goodbye. All right, so bring this tomorrow. At least tomorrow we're going to work on this. If not, it's kind of a bear. A lot of stuff to kind of graph and see. All right, so with that, have a good day. We'll see you guys tomorrow. All right, take it easy. Have a good day.